All right. In this lecture, we are going to be talking about the speed of computer algorithms and how we might be able to make certain calculations by computers a bit more efficient. So I don't really have much more to say about this. So let's move right into what we're going to be doing. So we have a couple of new topics to define here, new definitions. The speed at which a computer calculation is carried out depends primarily upon the number of floating point operations. A floating point operation is kind of cutely denoted flops. So I don't know, I kind of lamely came up with Flopsy the bunny here on the board, but I don't know. That doesn't have to be our mascot. I just needed something to put on the board, and I hope you enjoy it, Flopsy. Yeah, so floating point operations are really just the way that we kind of combine two different floating point numbers through either multiplications or additions. So to determine the number of flops in a calculation, it really just is a matter of counting up the number of additions and multiplications that are involved, given the definitions of how floating point numbers work in the first place. So here are some examples to keep in mind as we go forward and do some counting. So an addition, 2 plus 3, that requires one flop. If you have an addition of a positive and a negative number, that also requires just one flop, because a single floating point number can be a negative number, and adding those two numbers together takes one of these floating point operations, one flop. So addition and subtraction of two numbers that we know always requires one flop. Okay, the way that I want you to think about this is think of it as an addition, and then even if you have a subtraction here, you can always think of it as adding together two valid floating point numbers. So rewrite this first as a 2 plus a negative 3 to get it right. If x is unknown, however, the result might vary, okay? So 2 plus x requires one flop, but 2 minus x will require 2. If we don't know what x is to begin with, a computer is going to read this as 2 plus negative 1 times x, and I see 1, 2 flops there in order to get it right. There's the second arrow right there. 2 flops, not just 1. Whereas x could be a positive or a negative number or 0, and 2 plus an unknown will be just 1 flop. So that minus sign, if you have a minus sign, it may embed an extra flop if we don't know what the quantity is that's being subtracted. So be aware of that. Positive whole numbered exponents take a number of flops equal to their power minus 1. So if we have 2 to the 4, 2 times 2 times 2 times 2, we can easily see that there are 3 multiplications involved. 1, 2, 3, and that requires 3 flops. The total number of flops for an expression is going to govern the speed at which that calculation is carried out. So we have some simple counting exercises, but it's always very funny to see how these turn out. I would say that to get this right, it's very helpful to take a moment and rewrite the expression out, kind of in terms of how we know these floating point operations to work. So first, take a moment, take a step to write this clearly in terms of our operations. That will help us a lot when it comes to making sure that we don't miss any operations, especially around those unknown variables. So we could say that this is equal to 3 plus negative 5 times 0.0004, and then we're going to say plus minus 1 times x plus negative 2 times y. Okay, if you take a look, just double check, make sure this all works out. But you see how I've written this so that I can see specific additions and multiplications so that we can count more easily. It's okay if any specific number is a negative number in itself, but we need to make sure we don't miss any. So if I count these up now, I think this is right. There's an addition here, a multiplication right here, an addition here, a multiplication right there, an addition here, and a multiplication there. So I count 6 flops in total. And if you don't carefully write that out, you might miss something. It's possible, right? You might be able to count it up correctly and remember all the different rules, but I just find that this really helps. Having taught this last year, same darn thing. All right, next question. How many flops does it take for a computer to execute the following? So we have 1 plus x squared minus x to the 4 over x to the 5. So why don't we do the exact same thing and put this together. So we have 1 plus, and then we have an x squared is an x times an x. We can easily see the 1 flop for the x squared, and minus 1, 2 minus 1. And I'm going to write this minus sign now as plus minus 1 times, and then x times, I guess we don't need these x's in brackets. So maybe I'll just, it gets a little bit cumbersome is the only thing. So minus 1 times x times x times x times x. And the whole thing is going over a 5th power of x. So carefully counting these out, there's an x there and an x right there. Okay, so let's work on counting these out now. We have an addition here, a multiplication, an addition, a multiplication, some more multiplications right here. You can easily see that right there, the 3 flops associated with the x to the 4 right here. There's the extra flop because of the unknown x that's being subtracted here, okay? We have the 1 flop associated with the x to the 2. So you could write that out if you want to. Here are the 4 associated with the x to the 5 on the bottom, and we have one last one for division. Okay, so let's see. If we count all of these up, I've indicated them all with arrows here, but you can do whatever you want. We have 1, 2, 3, 4, 5, 6, 7 on the top, 4 on the bottom, and 1 to divide the 2. We count 12 flops in total. So we count 12 flops in total. Okay, and again, you can easily see all those different pieces, but it's nice when written out carefully to make sure that we have it. Okay, so yeah, as I said, right, it's helpful to write this out as a first step, but let's talk a little bit about why this might be important. Counting flops can let us compare the efficiency of different kinds of algorithms. The idea is this: if we can execute some code in a certain number of flops, let's call it big N, but we could also feasibly use another approach to calculate the exact same thing in N over 2 flops. That means we can do twice as many calculations in the same amount of time, and that will greatly speed things up. You know, any single calculation, any single expression with powerful computers these days might be able to be executed in, you know, a tiny, tiny fraction of a second. But that's not the point. Imagine like the kinds of graphics applications, video games, different kinds of things where you literally need to be able to do billions of calculations every second. In these sorts of cases, right, making sure that any one calculation is as efficient as possible is super, super important for the overall speed. You want to make sure the whole thing is as efficient as possible. So yeah, I forgot about this this kind of joke sentence down here, but for example, have you ever played a video game with a loading screen that takes forever? Perhaps the developers should have paid more attention to math 2130, etc., right? You just want to make sure that you're designing things as efficiently as possible. So oftentimes we can talk in terms of a parameter n and the number of different calculations, different operations that are involved in the calculation of an algorithm, and then actually speak in terms of our Bigo notation that we used a couple of lectures ago. So for example, there's a really cool example right here with regards to matrices. We know by taking linear algebra courses that sometimes it's helpful to row reduce a matrix into right? A triangular form of some sort. And it turns out that the number of flops, the number of operations that are needed in order to do this, in general, well, it'll vary depending on the matrix. And it might be slightly different for this one than another one. Maybe it's already in a better sort of situation or not. But in general, you need on the order of n cubed flops to reduce a general n by n matrix, which is kind of interesting, right? That means that as n increases, the amount of operations you need to reduce that matrix down, on average, in general, will increase according to n cubed rather than just n. So it's going to go up in this, this sort of cubic relationship. For more complicated functions, because this is always something that people ask, suppose you have like a sine of 2 or a ln of 3 or something like that. Those will tend to take many more flops than for simple calculations, and because that's simply because a computer will first use some sort of techniques to put that into a form that can actually be processed using multiplications and additions, such as Taylor polynomials and some other things that we're going to see in the weeks to come in this course. So that will take an extra step, replace it by a particular quantity for estimation purposes, but that quantity may have dozens of calculations associated. So I want to take that and go to a related, kind of an example, a special case of how we might be able to do this in a simple way. Polynomials are things that you've seen since probably grade 9 and grade 10. Just a series of different terms with integers for powers, so it's really repeated multiplications, and coefficients in front of each. There could be additions or subtractions, but this really seems to fit the bill for a conversation about flops. So if we want to take this example of a p of x here and write it so that we have a number of flops that stands out, so we can count it, okay? I've rewritten the expression for you in the notes right here. And if we go through and we count, we need a certain number of multiplications right there. There's more multiplications here, 2 of them for the x cubed plus another one between the coefficient and the x. We have more right here, and we have another one right there. So it looks like we have 4, 3, 2, 1. We have 10 multiplications in total. And if we count up the number of additions and subtractions, we have 1 right here, 1 right there, 1 right here, and 1 right there. Don't miss any, and don't overcount either, because -5 is itself a floating point number in itself. So we get 10 multiplications, and it looks like we have 4 additions or subtractions, for a total of 14 flops. The question is there a way to improve things a little bit? And there's a guy, there's an old nursery rhyme that's little Jack Horner sat in a corner eating some plum pie or something like this. And William James Horner, a British mathematician, came up with an interesting scheme in the early 1800s, providing us with a simple method to help speed things up. And what this does is it gives us a method involving sequential factoring. And what we do is we do this sequential factoring for successive powers of x. And in fact, what you do is you nest the necessary multiplications. So it turns out that writing out polynomials in the way that you and I are familiar with and that you've learned for years is actually an inefficient way of evaluating them. Horner's method is quite a bit different than that. It's going to make polynomials look very strange, but it turns out that it's much more efficient. And I want to show you how it works because it's actually super simple. So all you'll do is write out the polynomial in increasing order. I don't want to like reveal all of the secrets yet. So we have p of x equals, all I've done is list them, list the powers in increasing order now. And then once you've got that, I want to look at the first term where there's an x. Look, all subsequent terms are going to have x's in them as well. And what we're going to do is factor x out of those remaining terms. So factor x out. Factor x out of all terms but the first. And what you'll do is then look inside that bracket. And the first time you find an x term inside of there, you can then take an x out of those three and factor that out front. Essentially what you're doing is you're taking all of those multiplications and you turn them into a single multiplication outside the whole expression. So you're reducing at every single step. So we factor x out of this. So now factor x out of these. And we're going to continue doing the same thing. So I'm just going to say dot, 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 and repeat until we can't do that anymore. And the last time that you take x out, you have nothing more than a number left behind. Let's count the flops in the result. So if I take a look at this, we're going to look at the different multiplications here. I won't write them out, but you could if you wanted to here. Look at wherever a variable hits a bracket. X times, right there, I see a multiplication. 0.9 plus x times, there's a multiplication right there. X times, there's a multiplication right there. X times, there's a multiplication right there. The number of additions and subtractions, well, I have a plus right here, I have a plus right here, I have a plus right here, and I have a plus right there. So we've gone from 14 to a situation where we now have just 4 multiplications as well as 4 additions. And that gives us a total of just 8 flops. So we did a simple manipulation. We stored a polynomial in a very similar way. Well, a different way, but we stored the very same polynomial in a different way. And with that, you can see that they're the same, and yet we cut the number of operations required nearly in half here. And that's really, really useful, especially if that scales to a much bigger problem, where there are millions or billions of calculations involved. And so small savings like these can add up to a great deal of time. Okay, so let's generalize this, and we'll wrap up here. So in the general case, suppose we wanted to evaluate a polynomial, p of x equals a0 plus a1x plus a2x squared plus dot 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 plus an x to the n. We require multiplications and additions, and we can kind of list them in general. So take a look at this. We have no multiplications involved in the first term. We have 1 multiplication involved in the second term, the coefficient times the x. We have 2 involved in this term, and that's going to go up, and we have n involved in the last term. That's what this is right here. Okay, the number of additions in total, well, there's 1 in between each expression. So if you take a look, there's, I like the whole like purple versus green sort of thing here. We have 1 addition here, we have 1 addition there, and so on, and the last one's right there. We have 1 ahead of every single power, and so that means we have n of them in total. So let's think about this. The total number of flops that we would need to calculate for a traditional polynomial calculation is this. There's n. This is the number of additions that we have in total. And the number of multiplications we have, well, it's a little interesting, but I want you to process this for a second. It's the sum from I equals 1 to n of I, which is exactly what this is. That's just this term, okay? But written in a more succinct sort of way. 0 plus 1 plus 2, all the way up to the total number of the degree. That's what that sum is, and I'm adding n additions. We can actually show that this quantity is on the order of n squared. And that's sort of an interesting way of bringing a couple of topics together, but let's do it. You might not remember how to work with the sum so much, so let's rewrite it for a second. Sum from I equals 1 to n of I, write that in a bracket, plus n is equal to, now I'm not sure if you've taken a certain permutations and combinations, some people learn this kind of thing in high school, but I can actually take that first sum of the different integers of I that go up to n and replace it by something that is a quantity that depends on n. So by an identity, this is equal to, it's n times n plus 1 over 2. Okay, so this here, and this here, I'm going to write a little bit of a note on the side. These are equal by an identity. And I just want you to see an example, just in case you haven't seen this before, I want you to be convinced that this is true. So for example, you could take the sum from I equals 1 to 5, this would, of the different i's. This would equal 1 plus 2 plus 3 plus 4 plus 5. It's not hard to see that this is 1, 3, 6, 10, 15. And this is indeed, if I think of n times n plus 1 over 2, this is 5 times 6 over 2, i.e. The property holds. And that's actually true no matter what the n is. It could be 5, it could be 50, it could be 1,000,000. So I'm just going to put this in a little bit of a cloud off to the side so that we're happy with that in general. But I think most people will have seen this at some point in their lives. And if not, well, now you've seen it. So you can be happy with that. I've tried my best to educate you on an interesting property of sums. Okay, so this is the number of flops. And yeah, we want to show that this is on the order of n squared. So to show this is big O of n squared, take a limit. Go back to a couple of classes ago. Remember how this goes? We're talking about something that's away from 0 because it's a quantity of flops. That's like numbers that are growing with increasing amounts of n. So we're not talking about a quantity close to 0. We're talking about a large parameter that might, in general, be something that we treat with the other definition of big O, the one that uses the limit as n goes to infinity, that sort of thing. So we're going to use that, the limit as n goes to infinity of the number of flops, so that's n plus 1 over 2 plus n. I'm going to take that, I'm going to put it over n squared, and we want to show that this equals a constant. So this is going to give me limit as n goes to infinity. We get n squared, just evaluating the expression up here, plus n squared over 2 is what we need there, plus n over 2, plus n over n squared. I can divide all quantities by n squared. To simplify, this is really just first year calculus techniques and so on, but this is going to be the same as 1/2 plus, I am just going to make that clear by going 1 over n squared, 1 over n squared, like this, and then it'll jump out at us 1 over 2, and then 1 over 2n, plus 1 over n, it looks like, and the bottom, going to squeeze in here a little bit, is just 1. And we can see that in the limit, this term, 1 over 2n, goes to 0, and this term, 1 over n, goes to 0. We end up with just 1/2. That's a constant. It's a finite constant. So I'm going to write that over here. The limit is a finite constant. So we can see that the number of flops is on the order of n squared as n grows large. Okay, so that's a little bit of a demonstration. That means that as the degree of a polynomial increases, the number of flops is going to increase according to a quadratic function. Okay, that's the kind of how you want to view this. So the question is now, how do things improve when we rewrite polynomials using Horner's rule first? This apostrophe shouldn't be here, and that's really annoying to me. Using Horner's rule first. Okay, taking the polynomial as before, we can write it in this way. So nesting that, factoring out one one x at a time and going inside, inside, inside until we can't go any further. We now require, as we saw before in the one example, just n multiplications and n additions, and that gives us a total number of flops that's not hard to calculate. This plus this equals 2n flops in total. Okay, in other words, to calculate a polynomial of degree n, this technique of using Horner's rule changes a calculation that requires on the order of n squared flops into a calculation that requires just O of n. It's obvious that this is O of n because, I mean, I could write it in 2 lines. This is big O of n, since if I take that quantity and do the exact same thing, this time it's super, super easy. The limit as n goes to infinity of 2n over n is the limit as n goes to infinity of 2, which is 2. Again, it's a constant. And so we can be confident that using Horner's rule now makes it so that if a polynomial increases in its degree, the amount of steps you need to process that polynomial now only increases linearly rather than quadratically. That's huge, okay? Especially as n grows large, the savings from that is massive. And that's where the importance is for this. So that's about all I have to say for today. Some interesting stuff there. You never thought you'd be coming to university and counting as part of your degree. But I'd say that some of this stuff is really interesting, and that some simple processing, writing a polynomial in a slightly different way, can be done to great benefit. So hopefully that makes some sense. Spend some time with those for you to try problems and those from the last section as well. Get those down, and I hope that this section treats you well. We're going to be talking a little bit about some different stuff in the next few lectures. So get ready. We're going to be getting into the heart of the course soon and talking about various algorithms to solve different kinds of problems. I want to say goodbye. Thanks to the guest appearance from my terrible drawn bunny, whose name is Flopsy. What can I say? It's a lot of fun. I'll see y'all later. Bye, everybody.